That's great. And I might switch between screens. You'll let me know. We've got a couple of minutes. Will you let me know when everybody's there? Did you have a... Are we ready to go now?
Yeah, that's all right. Just start though. That's 9:30, I think.
Yeah.
Yeah, you can start.
Okay, fantastic. Well, we will get started. So just everybody. My name's Alex, and I work for a company called No Problem, and we'll just start today with a karakia. So, onahia te pō whiri marama, tomakia te ao whatu tangata, tātai ki runga, tātai ki raro, tātai ahurau, haumae, huie, tai ki. Okay. We will get started. So I thought we would start today's little session with this quote from the famous John Dewey. So John Dewey was a well-known educationalist, and he said, if we teach today's students as we taught yesterday's, we rob them of tomorrow. So I thought this was quite topical as a little quote to start, because maths education has been very topical in the media at the moment with the announcement of the direction of the new curriculum and the funding of the resources. So I think ultimately this quote is quite timely, because as these changes are coming in, I think it's really important as educators that we don't sort of do a throw the baby out with the bathwater type situation, but make sure that we're kind of utilizing the opportunities that we possibly are going to have sent our way, so to further help our students. So because ultimately, I think the idea of for us as educators, particularly in the math space, is to make sure that we are actually preparing them for a 21st century world that they are going to face, right? So forecasts are predicting that 80% of our future jobs are going to require at least base level mathematics. Right? So if we think about kind of some of the fastest growing industries right now, we have things like tech, right? All underpinned largely by numeracy and mathematics. So these results here that you're looking at, these are the TIMS results from the 2018 test, so the most recently released results. So TIMS is an international test that around 50 countries participate in. New Zealand is one of them. So TIMS stands for Trends International Maths and Science Study. So in New Zealand, we assess children in year 5 and in year 9. So these are the year 5 results. And so obviously what you're looking at here is New Zealand compared with some of our peer countries, and then compared with Singapore, who is the top performing country. Now, Singapore, you can see there in that red category, they have 54% of their students who would be categorized as being advanced. Now, through decades of study, what Singapore found was that children in that red category, that advanced level category, they possess a set of attributes or characteristics that make them perform differently to their peers. And they've labeled them the 5 core competencies, right? So today's little session is really going to focus on what those core competencies are and how we can develop them in our lessons and in our classrooms, because that's the goal, right? We need all of our children to be competent with these 5 key attributes in mathematics. Now, just before we look at what those 5 core competencies are, actually, Jo Bowler and her team at Stanford University found that there were 2 other characteristics that made advanced learners perform differently to their peers in mathematics, and they are both related to mindset, right? So the first one is actually how children perceive the nature of mathematics. So children who are going to perceive the nature of mathematics to be about thinking, they are going to perform differently to children who perceive the nature of mathematics to be a set of rules or procedures that they have to remember and follow, right? The second one is how children perceive themselves as mathematicians, right? So children who perceive themselves as leaders, whereby they would be given a problem and they would go away and try to solve it, right? They would be happy to try different things, make mistakes, look for relationships, use metacognitive behavior, right? What do I know about this and this that might help me? Versus children who perceive themselves as followers, whereby they are given a problem and then they have to wait for the teacher to show them how to solve that kind of problem, and then they would go away and follow the steps. So two things, right? How children perceive the nature of mathematics and how children perceive themselves as mathematicians. And both of those things are so important to be aware of as teachers, because they are both ultimately related to the culture that we set around mathematics in our classroom. So we have such an opportunity to change those two attributes for children in our classrooms. So the 5 core competencies that Singapore identified advanced learners having are visualization skills, generalization skills, number sense, metacognition, and communication. Now, ultimately, it doesn't matter what the mathematical content is of our lessons, right? So whether we are teaching measurement or whether we are teaching fractions, right? As long as our lessons are designed in a way that is going to be developing these 5 things in children, then they will always be growing as mathematicians, okay? So now we can get into the good stuff, right? The first one is communication. So communication is a critical skill. Oh, I don't know why it's doing that on that slide, right? Communication is a critical skill for children in mathematics. So maths is ultimately a language, right? And what happens is that we only develop one part of the language acquisition of mathematics for children, right? So if we think about learning a language, right, let's say any language, French, for example. If I gave you a French text and I said, I want you to find the meaning in this text, right? Lots of us would be able to read through it and find some sort of meaning, right? We'd be able to look for familiar words. We would be able to look for patterns. It would be much more difficult if I gave you an English text and I said, I would like you to translate this into French, right? You would have to have a much deeper understanding of the language to be able to do the latter task. So what that looks like in mathematics is all the time we give children the problem, right? And it's their job to solve it. So it's their job to find the meaning. What we don't do is we don't give children the abstract maths and ask them to put the mathematical language around it. So one way that we can develop that second part of the language acquisition of mathematics is by asking children to put the language around maths. So this is a good example of how we can do that. So we're going to have a go at doing this. So can you write a word problem for 76 divided by 8? And you have to make it produce the answer. The answer for your word problem needs to be 4. It needs to be 9. It needs to be 9.5, and it needs to be 10. So 4 different word problems. How can you put the language around 76 divided by 8 so that it can produce these 4 answers. You're not allowed to do any other calculations, and you're not allowed to add in any other numbers, right? It can only be 76 divided by 8, so no other operations, no other numbers. And the way you put the language around that calculation, you need the answer to be 4, 9, 9.5, and 10, okay? So you don't have to do this by yourself. You can do it with the buddy sitting next to you, or you can do it by yourself if you want to, but just have a chat, right? You don't have to write them down, but how could you put the language around that number? Set that calculation to produce those 4 answers, right? Off you go. Yeah, very common. Often when you first start, you think, maybe I've only developed one part of the language acquisition of mathematics, right? C is actually the easiest place to start, to be honest, because it's the exact calculation. So why don't you start there? We just put it at C to really throw you off, but have a go. Start with C if you're struggling, and then that might help you with the rest, right? So how can you make 76 a word problem, right? So that it's going to produce an answer of 9.5 or 4 or 9 or 10.
If I distribute it without having halves, then you're going to have I don't know how you change the original. The last one's I'm thinking rounded to the yes, yes, okay, so then you can get could be 9 side part yes.
Okay, sorry, because I am so aware that obviously it's quite a tight time and we've got a bit to get through, right? This problem is always really interesting because once you hear some of the examples, right, the maths in this is not difficult, right? The maths in this is probably year 4, 5 level, right? But it is a different skill to have to actually be given the maths and put the mathematical language around it. So when you first look at that, you think, she's nuts, right? 76 divided by 8 is never going to be 4, but it can be 4 if we are looking for the answer to be about did anyone figure it out? Remainder, right? So it would be a problem like 76 children are, well, we want to put 76 children into 8 equal relay teams, right? How many children need to sit out, right? If I had given you that problem, wouldn't have been a difficult problem, right? So the B, right, now that you know that, what would the B be? B is if you are looking for the whole number, right? So I've got 76 children and I want to put them into 8 equal relay teams. How many children in each team, right? Yeah. 9. C, that's usually the easiest place to start. And the important thing about that one, though, is to make sure that children bring you an appropriate context for decimals, right? Often when we are doing word problems in maths, we always want to use food, right? But food is not typically an appropriate context for decimals, right? So important that it would be a question like, I have 76 meters of ribbon and I want to cut it into 8 equal pieces. How long is each piece of ribbon going to be? And 10 is typically the most difficult one, right? That would be a question like, 76 children are going on a school trip. They take minivans, right? Each minivan can take 8 children. How many minivans would we need, right? Well, we would need 9 full minivans and then 1 extra minivan that would only have 4 children in it, right? So, yeah. So it's an interesting exercise for children to do, right? And this is quite an elaborate way of asking children to develop those communication skills and put the mathematical language around it. But it can be as simple as giving a mathematical representation and asking children to put the mathematical language around it. Or it could be where you just gave them a calculation, right, and ask them to put the mathematical language around that. Or if you were doing 3 times 4, for example, right, just asking children, where would you use that calculation in real life, right? Well, I would use that if there was 3 tables and there was 4 seats around each table, and I wanted to know how many chairs I needed to get out of the hall cupboard, right? Those sorts of things. But it is a really critical skill for children to be able to develop. Okay. The next one is around, I must, admittedly, I've used these slides to do another presentation a little while ago. I thought it would just copy over nicely without the background stuff. But the next one is metacognition, right? So what do we mean by metacognition? Because it is such a buzzword, right? Metacognition is really that ability to have an internal dialogue, right? It's that process of being able to think about thinking. So if we give children a problem in class, what we don't want to see happen is that children just jump straight in and solve the problem without first thinking about it, right? So they jump straight in and they use a procedure. Column methods is a great example of this, right? Once children are really good with column methods, often what happens is they stop using that metacognitive behavior, right? And they just jump straight in to use a procedure, and it might not always be the most efficient way to solve a problem, right? So developing metacognition for children in lessons is going to look like children who will kind of consciously think to themselves, what is the most efficient way to solve this problem, right? How do these numbers relate to each other? Or what do I know about addition and multiplication that could help me here, right? But we also want to take children that step further and actually ask them to reflect on what they did after they've solved the problem as well, right? So we want them to develop that behavior to be able to say to themselves, was that the most efficient way to solve the problem, right? Did I really need to do that? So metacognition is very much about children being able to make good decisions in maths as to what will be the best approach to solve the problem. So we're just going to have a look at this little one here, this question here. So Tama and Ravi gathered 360 tuangi. They packed them into 12 buckets for their family and friends. How many tuangi are in each bucket, right? So if we have a look at this problem, right? Class, what do you think would be a useful operation for solving this problem? What would be a useful operation for this one? We're likely to use division, right? Why would we be using division, do you think, class? Because we've got a group of 360 and we're going to share them into 12 buckets, right? Perfect. So does that mean I can just put 5 in one bucket, 100 in another bucket, would I be sharing them out like that? Would I be doing that, class? No, I wouldn't, right? Somebody is surely going to say, no, you have to share them equally, right? But how do you know we need to share them equally? Is that an assumption that you've made? Oh, our friend Ruby over here says, doesn't she, right? Each bucket contains the same number of tuangi, right? So critical when we're teaching that we make sure that we are explicitly modeling how to read the information and process the information, and we don't kind of model assumptions for children, because we see it all the time and then they don't kind of test very well. So what I would like you to do, class, again, is work with your buddy, right? How could you go about solving this problem, right? I'm not looking for just the answer. What I'm looking for is, could you see if you can find multiple ways to solve this problem, right? In our friends in our lesson, in the book that we're about to look at next, they've found 3 different ways to solve this problem, right? So if you would like to challenge yourself, you could see if you could come up with 3 different ways to solve the problem. Otherwise, you can just see how you would solve the problem, right? Off you go.
We can always jump to what we like. 100, 100, 100.
I would go for
That would work. I know. It would be hard. That's why I just erased it. Because I jumped.
Well, we could probably look at it and knowing do it into 3.
Yes. Yeah. And then about 20, 20, 20. Yeah. And then that gives us 3 buckets, and then from there you could divide both of those into 4. Okay, yeah.
Okay, class, sorry to interrupt you, right? Let's have a look and see how our friends have solved the problem here. So one way that as teachers we can help children to develop metacognition in our classrooms is by always presenting them with multiple ways to solve a problem, right? So we are really limited by our own thoughts, right? We only know what we know. So it is really important that we expose children to multiple ways to solve a problem. So if we have a look at how our friends have solved this problem, right? Let's have a look at method 1. That's Charles's method, right? So Charles has used the place value discs to represent the tuangi, right? And we can see that Charles has thought, right, within the 360, that he can see 3 groups of 120. Why do you think Charles thought it was useful to know that 360 was the same as 3 groups of 120? Why would that have been useful, do you think? Right? I think Charles might be giving us a clue there, right? What does Charles understand about 120? 120 is the same as how many tens?
12.
12 tens. Why would it be useful to know that 120 is the same as 12 tens? Oh, I think it might be because we have 12 buckets, right? So that means 1 10 for every group of 12 tens, right? 1 10 would go into each bucket, right? So that is going to be 3 tens in each bucket. 3 tens is the same as 30, right? 30 tuangi in each bucket, okay? If we look at method 2, right? Lulu's method is using the long division algorithm, right? And then if we come down to method 3, right? What do you think Ravi's method is in method 3? Right? it looks like Ravi has thought, right, dividing by 12 is quite tricky, right? It is quite a large number to have as the divisor. So I think what Ravi has looked at is he has used his factors of 12 in order to help him solve the problem, right? So he has first drawn a bar that represents the whole number of tuangi, right? 360. He's then split the bar into 3 equal groups, right? And then he has split those 3 equal groups by 4, right? And that has given him 12 equal groups, okay? So having a look at that, right, we can see that method 1 and method 3 are really more number sense type methods, right? They work in today's problem because of the numbers that we are working with for this problem, right? Method 2 is really more of a formal written method, right? So metacognition, right? Or if I said to you actually in this example, right? Would these methods always work, right? Or do you think that they just work because of the numbers that we've been given today? Let's look at Ravi's method. Do you think Ravi's method would always be a useful method? Class? Why would it not always be a useful method?
A tidy number.
Yeah.
Right? Would it work if the divisor was a prime number, for example? No, right? So important, right? Metacognition is about recognizing what we can and can't do with number, right? So we want children to always be developing this internal dialogue, right? Rather than going, say, straight to long division or straight to column methods, right? We want them to be asking themselves questions like, oh, what do I know about 360 and 12, right? Is there a relationship here that can help me to solve this problem? So presenting children with multiple ways to solve the problem to develop metacognition is not about every child having to rote learn every method that's on that page, right? What it's about is gently exposing children to other ways of thinking so that if they encounter a similar problem later on, they might be able to say to themselves, oh, actually, I remember we used factors to solve that problem that time, right? I wonder if that would be useful here, right? So it's metacognition is about, yeah, making sure that children can develop that internal dialogue so that they can think about the problems that we're presenting as opposed to just being stuck with one way to calculate an answer. Okay, the next one is number sense. So number sense is really our ability to be flexible with number, right? To understand what we can and can't do with number. Really, it's about kind of being able to be fluent, right? So we are going to do a little activity now to illustrate how we can help to develop number sense for our children. So what I would like you to do is we are going to do this in pairs, and hopefully you have some digit cards in front of you. So you need one set of digit cards just between 2 of you. You're going to do this one in pairs, so you only need one set of digit cards. And the digit cards should be just 1 to 9. So if you've got a 0 in there, can you just check you don't have a 0 in there and take it out if you do? Okay, so what you need to do is you need to use the digit cards and you need to follow this structure. So you need to make equations that are a 2-digit plus a 2-digit equals a 3-digit sum, right? So a digit card needs to be in each of those spaces to make an equation that makes sense. And if you find one, can you just call it out to me or tell the facilitator, and they'll be able to tell me and I'll pop it up on the little whiteboard. Okay, off you go.
I think I'm the
You look like a 3. 64 plus 75.
I'm not sure.
Okay, 64 plus 75 makes what?
139.
139, okay. Carry on.
I like this. Yeah. Oh, yeah.
there.
We need the answer as well.
Not carrying.
You know, I'm playing people like
65 plus 78.
Okay, 65 and 78, and that makes what?
143.
140.
Yeah.
143.
Oh, sorry, what did you say?
143.
Okay, fantastic, class. Carry on.
73 plus 92 is 165.
73 plus 92 is 175, okay. Oh,
65.
60. What did you say, sorry?
165.
65, fantastic. Okay. So
Out of the box.
I'm wondering, do you think it's possible, what would be the smallest sum that you could make, right? See if you can make the smallest sum, right? Remembering it has to follow the same structure. So it has to be 2-digit plus 2-digit equals 3-digit sum, right? So the smallest one we've made so far is 139. What would be the smallest possible sum, do you think? So carry on. See if you can make the smallest possible sum.
Smallest possible sum. All right, well, we can take what we already know. We need 3, 4, 5.
Yeah.
Yeah, no, that's
Oh, come on. Not very good.
oh.
You have to be able to get that.
No, I'm
Higher.
But
it's a new way. Okay, call it out, Mel. Yeah, 136.
And 136?
Yes, we got 52 plus 84 equals 136.
Okay. Do you think that that's the smallest possible sum, or do you think that we could make a sum smaller than that?
We've got 83.
Oh, yeah.
83 plus 46 equals 129.
Yeah.
Wow.
All right.
Equals 100 and what, sorry? 29. Okay. You think that's the smallest possible sum? Class, do you think we already know what the smallest possible sum would be?
Yeah.
How do you know what the smallest possible sum would be?
1, 2, 3.
You think it would be 123? Okay. So why would it be 123? Because if we're going to make the smallest possible sum, we would want the smallest digit in the column with the greatest value, wouldn't we? Right? So that would be the 1 in the hundreds column, right? In the 2 and then the 3, okay? But right now, do we think it's possible to be able to make 123?
You need more ones and twos.
Yeah.
So 1, 2, 3, 4 you could not make.
No, because you would need
1, 2, 5 did not make. 1, 2, 6 did not make.
That's too big.
1, 2, 7 did not make.
2, 8 you can't.
No, just a 1, 2, 9. Because you could do 1, 2.
I think we've got it.
1, 2, 6.
54 and 69.
Ah, okay. 54 and 69. Does that make 123?
We think so.
Okay, class. Right. What would be the greatest possible sum you could make then? So far, we have made 165 as the greatest sum, but do you think it's the greatest possible sum? Right, class, keep going. See if you can find the greatest possible sum and be able to reason as to why you think what your answer is.
Sorry, what was the question?
And then you probably want.
No, I don't think you could either. I was just, I wonder if 187 is the possible. Or 198. I wonder
7 and 9.
if it can't be anything than that.
But it's nearly here, right?
We've got 92 plus 84 is 176.
Yeah.
92 plus 84.
Is 176.
And you think that's the greatest possible sum? Or do you think you could possibly make one greater than that?
We can.
I do think having that 9 and the 8 is the best you could do
Yeah, that's the
here.
highest you can do.
Oh, no, you'll only get to an 8.
You can't go bigger than a 6.
Yeah, I think it might
No, I
be.
think that's about what you have available. I think that's about
Okay, class, I don't mind if you keep moving the little cards around while I'm talking, but just because we are short on time, I am going to just carry on. But the important thing to understand here is how does having good number sense, right, help you with this activity, right? So if you have a look at the sums that we have made so far, what do you notice? Right, they all are, right? They all start with the 1 in the column, right? Now, very quickly, right, more advanced learners or children with strong number sense, right, will be working systematically, right? And they will very quickly recognize that the 1 always needs to be in the hundreds column, right? That is not a coincidence. Is it possible if you're adding a 2-digit number to a 2-digit number, if I said you can use any numbers, would it be possible to make a sum that's 200 and something, do you think?
No,
Why not?
Because
you have
less than 100 and less than 100 is never going to
Right,
get you.
because if I said that if you were going to add the two largest 2-digit numbers, it would be 99 and 99, right? What's 99 and 99? 198, right? So it is never possible to cross the barrier if you are adding a 2-digit number to a 2-digit number, right? So it always needs to be, the 1 always needs to be in the hundreds place, right? So if we have a look, is 176 the greatest possible sum you can make, do you think, class?
We thought so.
Yeah,
Why
we
do
thought
think so?
Because we get the 9 and the 8 and the 10s place. That's the
use the
largest.
7, the 6. Yeah.
Interesting, the strategy for finding the greatest possible sum is different from the smallest, right? So the smallest, we know what it would look like, and we start with the sum and we work backwards, right? For the greatest possible sum, we understand that we would want to have the 2 highest digits or largest digits in the column with the greatest value, right? So start with the 9 and the 8 in the tens column. That would make 170 something. Surely then we could carry over from the 1s column, and we could make a sum that's 180 something, couldn't we? Oh no, we can't, can we? Because we've already used the 8. So it has to be 170 something, right? And so the next, we would want to have the next highest digit in the ones column, which would be the 6, right? So do we agree that 176 would be the greatest possible sum? Right? So children with poor number sense are not likely to be working systematically in this task, right? What they would be doing is just kind of moving the cards around and doing more of like a trial and error type process. The digit cards make a huge difference for accessing this particular task, right? It's much more difficult if we just ask you to write the sums, right, without the support of the digit cards. You see lots more mistakes happen if we make you do it that way. But activities like this really encourage children, really encourage that skill of number sense, right? Because obviously the skill in this is just to learn to add a 2-digit number to a 2-digit number, right? That's the objective. So I could have just given you a worksheet of adding any old 2-digit numbers together, right? But your experience with it wouldn't have been as rich, and it wouldn't have kind of encouraged that development of number sense, right? So it's an important skill to look at. I'll just switch back my screens. Right. So number sense, just to reiterate, right, I'll give you some other examples of it, right? So if we looked at the number 6, right, if I asked you to tell me everything you know about the number 6, all of you would feel really confident in doing that, right? So you'd be able to tell me that it's 1 more than 5, or it's half of 12, or it's 3 groups of 2, right? We are all really secure in our number sense of 6, right? We know where 6 lives in the world of number, right? Now, if you look at the next example, right, people with strong number sense will know that 30, 29, and 31 is actually just the same as 30 plus 30 plus 30, right? So we know that 29 is 1 less than 30, and we know that 31 is 1 more, therefore it's the same as 30 plus 30 plus 30, right? But children with poor number sense, what we might see happen when they were given this task is we might see them start to do a column method, right, to solve this problem. And effectively, they would have used a procedure that wasn't efficient and wasn't necessary to solve this problem, right? So the next one is a classic example, right? 2.8 times 10, and we see children say, oh, when you multiply by 10, what do? Oh, you just add the 0 on the end, right? And that is the worst kind of trick that people teach children in mathematics, because it is not accurate, right? It doesn't work when you are multiplying decimals like this, right? So it's a really important one, and it tells us that the children haven't conceptually understood what multiply by 10 means. And the final one is number bond work is critical for being able to have strong number sense, right? That understanding of being flexible with number, right? So if you're looking at 51 times 3, right? So 51 times 3, right? The most useful way to split 51 would be 50 and 1, right? But if you're doing 51 divided by 3, right? Splitting the number 51 into 50 and 1 is not the most useful way to split the number, right? We would want to split into 30 and 21, right? So number bonds are so critical for developing students' fluency and number sense, right? We need them to understand how they can manipulate numbers to do useful things in mathematics. So that one's a really important skill for our children to learn in order for them to develop really strong number sense. Okay, right, the next one is generalizations, right? So what we mean by generalizations is it's this ability to use what you do know to help you figure out what you don't know. And it's all about making those connections. So maths is a really interconnected subject. And the more connections you can make, the less you have to remember. So children who struggle with mathematics are often children who are going to struggle to make generalizations. So what happens is they see all of the learning as being discrete or in isolation, and it overloads their memory, right? So it is really critical that we don't leave the ability to make generalizations up to chance, right? We actually have to explicitly teach children how to do that. So if we look at this particular picture here, right, we can see that this picture is an illustration of the 3 times tables, can't we? Right? But we can see that some cubes are purple and some cubes are blue, right? What do you think is being illustrated in this picture? Just talk to your friends or just have a think for 20 seconds by yourself, right? What do you think is being illustrated in this picture with the different colored cubes? Hopefully you can see them, Ken.
I'm colourblind, they're all the same.
Yeah.
Well, it's not so helpful.
Yeah.
Can't see them.
Be like
Oh,
yeah. That 5 times 3 is 15. So I know that 5 times 6 times 3 is 5 times 3 plus 1 more 3.
Okay. Sorry to interrupt you. Right.
Oh, okay. Is that it?
What this image is illustrating, right, is it's teaching children how to use what they do know, right? How to use known facts to derive unknown facts, right? It's about helping children to make those generalizations. So generally speaking, right, all adults and children will know their 1 times, 2 times, 5 times, and 10 times tables, right? So we can use those known facts to help us derive unknown facts, right? So known facts are in purple, unknown facts are in blue, right? So we know 1 times 3, we know 2 times 3. To figure out 3 times 3, we would do 2 times 3 added together with 1 times 3, right? 4 times 3, most efficient to do 2 times 3 and double it, right? 5 times 3 is a known fact. If we looked at 7 times 3, right, we're going to decompose 7 into 5 times 3 and 2 times 3, right? By the time we get down to 8 times 3, it's most efficient to take 4 times 3 and double it, right? Why then would 10 times 3 not be shown as a known fact, do you think? What we want children to see is actually the most efficient way to figure out 9 times 3 would be to say 10 times 3 subtract 1 times 3, right? So it is really critical that we don't leave these things to chance, right? These are the research behind how we learn facts and how we learn operations actually was done by, well, there's a lot of research around it, but some of the most recent research is done by a man named Arthur Barudi, and he writes, it's actually a really good paper, it's really interesting. But he said there's 3 phases to learning operations and facts, right? Phase 1 is counting. Phase 2 is figuring out, he calls it. And then phase 3 is remembering, right? Remembering is the goal. But when he talks about remembering, what he really means is knowing, right? The same way you know your name, right? You're not having to pull that from your memory. If I ask you what 2 times 6 is, you're not having to pull that. That's like an automatic response, as opposed to if I ask you what 7 times 8 is, right? You might be able to respond pretty quickly, but you're not going to know that the same way that you're going to know 2 times 6, right? So there's this phase in the middle. What we do often in class is we go straight from phase 1 to phase 3, right? We start by skip counting for children, and then we go to rote learning your times tables. But what's really critical, Baruti says, is we have to teach children how to make generalizations or how to derive facts when they don't instantly know them, right? So the strategies are always the same. These key things work for any times table, right? So doubling, decomposing facts, and using your known facts are all going to be able to help you to derive those unknown facts. But we cannot leave these things up to chance, right? We have to actually explicitly show children how to make generalizations and learn that skill in mathematics. Okay, and the last one is, how can they, right, right? Visualization. So advanced learners have really strong visualization skills, right? So ultimately what that means is they can picture the mathematics, right? They have the visualization means that you have the ability to see beyond what the eye can see, right? You can picture it in your head. So an example, right, would be if you looked at this question, right? One thing we would want to say is, so what do you notice when you add consecutive odd numbers, right? What do you wonder? So one way that we can encourage children to develop the ability to kind of like make visualizations and to think beyond that is we might always ask children, right? What can you see, or what do you wonder, or what do you notice, right? So have a go at this question and just talk to your buddies, right? If you're adding up odd consecutive numbers, what do you notice, right? Have a look. Okay, class, sorry to interrupt you, right? What did we notice when we started adding up odd consecutive numbers? Did anyone find anything interesting?
Odd, even, odd, even. Your answers are odd, even, odd, even.
Okay, yeah, right. What about if I said to your class, what would it look like if we drew that, right? What would you notice now?
They're square numbers.
A square number.
Right? So if we visualize it, we suddenly see why, right? Adding odd consecutive numbers is going to produce the square numbers, right? So this picture is going to give the explanation for the mathematics, right? So children who can visually represent maths, right? It enables them to perform at much higher levels, right? When they can represent mathematics and they can represent relationships that are happening in mathematics, right? That is one of the skills we see children really struggle with, for example, word problems, right? If children can't visualize the relationship that's happening, they struggle to know what the calculations are that they need to make to be able to solve the problems. Right? So being able to visually represent maths and have strong visualization skills is going to make our children much stronger in mathematics. Okay, So what time am I looking at? Oh, yep. Okay, this finishes at 10:30, is that right?
No. Done.
20 minutes, what,
10:20.
10:20.
Oh, this finishes now.
Yeah.
Okay.
You got it.
Okay. Well, no, that's all right. We just won't do the last couple of slides because we got through what the 5 core competencies are. So I think ultimately, right, what we would want you to take away from this little session is that these 5 things they are critical for children to be able to perform at those top levels in mathematics, right? So again, it doesn't matter what the mathematical content is that you are looking at in your lessons, right? If you have got these things, if you are teaching to develop these 5 things in your children, they are always going to be growing as mathematicians, right? So they are really important, and they will be what move children from being just calculators into that true advanced learner category. Okay, right. That is it from me. Is there anything I can help with? Otherwise, I guess you guys have to actually go to your next little session.
We have morning tea, so that's okay.
Oh, right. Is there any questions that I can help with? Otherwise, you are free to go. Hopefully you enjoyed the session.
Yes,
Thank you so much.
No, no problem. Wonderful.
Yes, wow, good training. Just morning teas in the canteen.